introduce another one called Bishop routine solution. Okay, in this solution, we assume x1 is equal to x2, x1 equal to x2. Then we resolving the forces in vertical direction. You see, in vertical direction, this purple dashed arrow shown here. In this direction, we cancel. Okay, we don't need to consider about the external horizontal force U1, E2, so that we establish the vertical force equilibrium, right? And to avoid, you see, to avoid E1, E2, right? Then step by step, we arrive at here, which gives us the expression of the M prime. Okay, this is what we need. Okay, so with the M prime expression obtained, so we can write the general expression for the factor of safety. You see, for the factor of safety under the assumption by Bishop. Okay, so you can see that the error from Bishop method is usually less than 2%. Okay, it's quite accurate. So we will conclude that Bishop method is generally better than other method like Jambu's method, like what we just discussed, the Philinus method. Okay, this is normally this is the best one. Okay, we will see a lot in the example. Okay, maybe in next week's tutorial. And of course, we discussed about the gamma H if we change the U, the water pressure, by water head H multiply the gamma. Gamma means unit weight, right? And this is the elevation change of the H. Okay, so if we change it to express the water pressure by gamma H, we have another different expression. Okay, actually nothing changed. We just to use this one to replace the water pressure. Why we will do like this? Because we are going to introduce to you the Bishop and the Morgenstern chart, okay, which is very powerful. It utilizes the RU value, the U over gamma H, okay, U over gamma H. Then how to determine M and N? We just use the design chart very easily. It gives us the choices of different friction angle and the slope angle, right? The slope angle. So this is quite powerful. You see, we attached the table here. We can easily to refer to determine the M and N, and then determine the factor of safety. Okay, here the residual strength. We spend a lot of time here because I think this slide will be very important to make you more clear about the difference between the definition of peak shear strength, the critical shear strength, or the shear strength at critical state, and the residual strength. Okay, under which conditions we use the peak strength, and under which condition we will use residual strength. Okay, we discuss in quite detail. Okay, because the tau we normally use the Moore Coulomb failure criterion, right? The tau will be equal to C phi C prime plus sigma M prime tangent phi prime. Okay, if we talk about the effective stress approach, okay, but this tau, you see, we can say it is tau F, failure, right? But this tau, how to determine it? Using this slope, this phi, we will use the phi determined from the peak strength, like this straight line here, or we will use the residual line here. Okay, they will be different. As I said to you, discussed with you, for the peak strength, we normally adopt it for the newly filled or newly cut off slope, which is new. Okay, it hasn't experienced any failure before. Okay, but for the residual one, we normally adopt it for the slope which has failed to some degree or to some extent in the history. Okay, which means it has moved already in the history. Okay, so you can see that the residual one will be smaller than the peak one, right? It's quite reasonable, right? If the soil or the slope is totally intact, we can imagine that the strength will be higher, right? So for the unintact or it has experienced some failure to some extent, I mean, for those kind of slopes, we expect a smaller strength. Why? Because for the residual one, it corresponds to a larger shear strength top as the epsilon. Okay, you can see this with the increase of the shear strength, the soil strength, or we call it mobilized shear strength, mobilized shear friction or shear stress. Okay, to be more specific, mobilized shear force or shear stress, it will increase at the beginning. Then with the increase of the strength, it will come down. You see, so for the failed slope, actually, we expect to use a smaller shear strength, like the residual strength, okay? So we will have another line in the middle, which we call if the phi CV, okay, critical state. So when to use critical state, this is not that straightforward, okay? It depends on the engineering judgment, okay? Engineering judgment. Maybe we prefer to use a critical one because it is more conservative compared to the peak one, okay? So, but this one is more related to our engineering judgment, okay? No absolute definition. When to use this one, when to use this one, okay? No absolute definition and a conclusion, okay? And we also discuss together about the ring shear test, okay? Ring shear test. This one you are not familiar before, okay? Because we don't have this one in our soil lab, and this test apparatus is not that common, okay? But it is quite useful to determine the residual strength, because this strength corresponding to residual strength can be more than 50, okay, even larger than 100%, okay? Normally, like the direct shear test, like the triaxial test, can not achieve this this large strength level. So we use ring shear test, okay? Okay, we discussed already here and discuss about the stability chart, like the definition of critical height, okay? If you use this design chart, the factor of safety will be defined by H, which means the current here, the current height over critical height, okay? So you see here, for this design chart, the definition of the factor of safety is quite different with what we discussed before, right? We use the limit equilibrium, like the equilibrium of moment of force before, but here it is defined in terms of the height of the slope. But for this design chart, actually, it contains two layers, or we can say two parts of slope. It can give us more flexibility to describe the factor of safety with more complicated condition. Okay, you see alpha angle here, beta angle here, right? So this is another powerful design chart we can use for a more complicated case. And okay, so for this one, I think we discussed a little bit last time, this example, I think so, if I remember. You see from the Taylor's chart, it is equal to this value. And from this stability table, I mean this one, actually we can get the result here in terms of the ratio between different height. Okay, they are quite similar, okay? Of course, we cannot say they are totally the same, of course, but they are quite similar, okay, from different from different methods. Okay, they are comparable. Okay, you can see this one factor must be larger than 1 if it is safe, right? So today we are start with so-called plane translational sleep. Okay, as I mentioned to you in the beginning of this lecture, this kind of sleep is quite common in Hong Kong. The reason is the bedrock depth in Hong Kong normally is not that deep. Okay, it's not that deep. So the soil can be easily uh, dissipated on top of this bedrock. Sorry, deposited. Okay, on top of this rock surface, and along with this surface, the soil will slide along one direction. Okay, along one direction without any rotation. Okay, this is a point. If the translational slip has no rotation, okay, with it slide along one direction. And if we consider the force equilibrium, okay, as shown here, of course, they are the same. The shear strength will mobilize, okay, will mobilize with the increase of the strength. Okay, this is the definition of the shear strength mobilization. Okay, you see, if we still use this Moore-Coulomb criterion to define the tau f, okay, tau f, and this tau, we can say it is tau m, okay, mobilized or current one. We have a factor of safety here, right? So the factor of safety is defined between the failure strength. Okay, this failure strength, as I mentioned to you, it can be determined by the peak value, critical value, and residual value. Okay, it depends on which case we are concerning. Oh, okay, and this is tau. Okay, it's tau m. And if we choose to use the effective stress approach, all here you see we have prime here. We should use the effective friction angle. We should use the effective cohesion, and we should use the total stress to minus the pore water pressure to get the effective stress. Okay, so this is the definition of tau f. Depends on which one you are going to use. So first of all, we are going to discuss how to get one general expression for factor of safety for this kind of condition, the plane translational slip. Okay, so you see we have a long soil mass here, the yellow one, okay, a long one. So we can assume that the length along this direction is infinite, okay, is infinite. And we just see the height or the thickness of this soil mass is equal to z, okay? And we have a water table here, as shown here, the blue dashed line, the water table. The height of the water table is equal to mz, okay? M is just a ratio, okay, mz. So m will be changing between 0 to 1, right? Between 0 to 1. Okay, of course, we will discuss more complicated scenarios in later slides. Here, m will be changing between 0 to 1. And you see, the water table is parallel to the soil surface here. The water table, they are parallel, okay? So with this in mind, let's see. First of all, how to determine the pore water pressure at the sliding surface. Okay, here we have the rock, right? We have the rock. The soil mass will slide along this direction. Okay, along this direction. So inside this soil mass, how to determine the pore water pressure at the surface of the rock, or we can say at the sliding surface. How to define this pore water pressure? Okay, this pore water pressure. Okay, so we will draw a flat net, flow net first, a flow net. And you see for the flow net, we have the flow line as shown in this direction. The flow line's direction will be the same to the sliding direction, okay, parallel to the soil surface and parallel to the sliding surface, okay? According to the definition of the equal potential line, okay, I think you have already learned this one in chapter 2 of soil mechanics, okay, the seepage part. So equal potential line is perpendicular to the flow line, okay, it's perpendicular. This is 90 degree, okay. So we can draw this kind of flow net here, okay. With this flow net, how to determine this U? Okay, I just want to help you to recall your memory in the soil mechanics. The so-called equal potential line means the total pressure along this line is the same. Also, for this line, the total pressure, or always say total water pressure, are the same. Okay, and let's express it in this way. For example, this point is 0.1, and this point is 0.2. Okay, so goal is to determine the pore water pressure at this point, 0.2. Okay, so H, the water head total, the total water head of 0.1 is equal to, okay, is equal to the summation of three parts. The first part is elevation pressure. Elevation pressure plus pressure, I mean the total water head, okay, let's say this H is the water head, is equal to the elevation water head. Sorry. Okay, I see one message from the Zoom. Okay, let's continue. The total water head is equal to the elevation water head plus pressure water head, P. Okay, if you still remember the concept in the soil mechanics, plus HV1, the first point. This V means velocity, okay? Total pressure head, total water head is equal to elevation head plus pressure head and plus the velocity head. Okay, this is the three parts for the total one. So we can just write another equation for the point 2. Okay, it is still composed of three parts. So first of all, we see the equal potential line, which means total water head of 0.1 will be equal to total water head of 0.2. You see, they are equal. Then, because the flow line are joined here, you see, along with the surface, the soil surface, or the sliding direction, along with this direction, all the water flow velocity on the equal potential line is the same. Okay, the water flow velocity here, water flow velocity here, they are the same. Okay, so these two are equal as well. Okay, HV1 is equal to HV2. So we can draw another one. We can write another equation. Is equal to HE2 plus HP2. Okay, they are equal, right? This item is equal to this item. Okay, no problem, right? And the goal for us right now is to determine the pore water pressure at point 2. which is just HP2, the pressure head. Okay, this is what we are going to arrive at. Okay, we want to get this one. So let's see. HP2 can be written as this one, right? This one. HE1 plus HP1 minus HE2, right? And we can see that the pressure head of 0.1 should be equal to 1. It should be equal to 0. Why? Because it is at the water table surface. Okay, at the water table surface. So HP1, the pressure head of 0.1 should be equal to 0. Okay, so without this item, you see, the HP2 or the U is equal to the elevation difference between 0.1 and 0.2. Okay, elevation difference between 0.1 and 0.2. So it is quite clear now. The elevation difference will be equal. The elevation head difference will be equal to the gamma unit weight multiply the elevation difference. Let's say elevation difference. Okay, elevation difference. You see, the gamma is equal to the gamma water, the unit weight of water. Okay, W means water. And ZW actually is the same of elevation difference. Of course, elevation difference is ZW, is the, how can I say, the water elevation difference. Okay, water elevation difference is Z. So the question now becomes how to determine the Z value. Okay, let's see. Elevation means the difference along the vertical direction between 0.1 and 0.2. Okay, let's move 0.1 to 0.2 here. 0.1 and 0.2. Okay, they are the same. They are all the same. They are all the same because we assume this is infinitely long, right? Each point here is totally same to here. Okay, of course, similarly, the point here will be equal to here, to here, to here. Okay, so we can just move 0.1, 0.2 to here. 0.1 is this point, 0.2 is this point. Okay, so the elevation difference from between these 2 points is presented by this equation. Mz multiply cosine beta, then multiply another cosine beta. Okay, Mz is this one. You see, Mz. Okay, they are the same. Mz is here. Then Mz multiply cosine beta is equal to the length of this one, right? This one. Okay, this one. No problem, right? Mz cosine beta. Then another cosine beta, we come to here. Sorry, we come to here. This one. Another cosine beta. Finally, we get the length of the elevation difference between 0.1 and 0.2. Okay, exactly the same to this one. So far we actually discussed in quite detail how can we get the expression for U, the pressure head. In other words, we can say, okay, the pressure head of this point. Okay, so how to arrive here? Okay, one by one, we're from here, one by one, then we get it. We get here. So the thing is how to understand this one. Okay, and now we have the U equal to gamma W, the unit weight mz cosine beta square. You see? Okay. Until now, if you follow my explanation, I think it should be clear. Okay, but you can refer to my explanation in the recording. Okay, if necessary. Okay, and for the W, uppercase W means the weight of the soil. You see, we just take out one slice in the translational slip, this is just one slice with the green color, okay, with the green color. And for this green color, we assume the width, okay, is equal to 1, which means the unit width, we just to choose this slice, okay? It has a width equal to 1. So this weight is a line load. A line load again. If you still remember, we have another line load in the pile foundation, right? So for this one, if we draw it in 3D condition, for this cross section, it must have a like this, right? Like this. Okay. So the line load means unit length in this direction. Okay, unit length in this direction. We have the line load or the line weight of the soil mass, because we only consider the cross section here, the 2D now. We consider it as a 2D. Okay, so we ignore the length along this direction. Okay, we ignore it because we choose this one is also equal to 1. So we can call it the unit line load, okay, of the soil mass here. And for this one, the W is equal to 2 parts. The first part is the soil above the water table. And another one is the soil below the water table, right? And above the water table, the height is equal to Z minus MZ, right? Or we can say is 1 minus M multiply Z. Then multiply the total unit weight gamma. Okay, then multiply the width, which is equal to 1, right? And plus the height of the soil below the water table, which is equal to MZ, then multiply the saturated unit weight, because it is under the water table, which means it is saturated because it is submerged under water, right? So this one will be different with this one. Okay, in theory, they must be different, okay? So under with further arrangement, we have this one. This is expression for the weight of the soil slice here, as shown in this green slice here. Okay, so far we explained to you about the pore water pressure and the weight of the soil mass. Okay, we write it here, right? No problem, right? So we consider the force equilibrium in vertical direction. Okay, the force equilibrium in vertical direction. Let's see. I put the symbol here, the P soil from the left-hand side, the P soil from the right-hand side. It means the force from the soil and the force from water, okay, from the water. As I mentioned, in this direction, this translational slip is infinite long, which means the internal force along this direction, will be cancelled with each other for one slice, okay? Which means this one will be equal to this one, and this one will be equal to this one, okay? They are cancelled, okay? They are actually, I should not say they are cancelled. They are equal, okay? They are equal. They are equal, okay? They are equal. So you see, I only use one name, P soil, because they are equal, okay? P water, okay? So along the vertical direction, what we have now, what is remaining, okay? One, of course, is the weight, of the soil, right? The weight of the soil. And another one is the anti-force from the bedrock, okay? Below the sliding surface, okay? The anti-force below the sliding surface, which is equal to sigma V, because we are talking about the vertical direction. right? Sigma V. And sigma V is a stress, but this one is line load, right? So we should have another length for the sigma V. Sigma V should multiply the length of this side, you see, this side, which is equal to 1 over cosine beta. If we draw, okay, this triangle here, this one is equal to 1. The inclination angle of this slope is equal to beta, which means this one is equal to beta, right? So the length here, this side, is equal to 1 over cosine beta. Similarly, this length is equal to 1 over cosine beta, right? No problem. So sigma V multiply, as shown here, sigma V multiply 1 over cosine beta means the stress pointing upward. The stress pointing upward. Okay, it is just equal to the mass or the weight of the soil in the green part, in the green slice. Okay, weight. This is weight. Sigma V over sigma V multiply. Okay, 1 over cosine of beta is pointing to upward. Okay, they are equal. Why? Because these are only two remaining. Okay, only two remaining in the vertical direction. Okay, someone might ask me, if there is a sliding, we have a tau here. Okay, this tau will also have another decomposed force along the vertical direction, right? Along the vertical direction. Why? We only have these two, sigma V and W. We don't consider about the tau. Why? Because I explained to you, this sigma V actually is the resultant force, resultant force, okay, resultant force of tau and sigma n. Because on this surface, we have normal stress, of course. We have shear stress, of course. Then the shear stress tau and the normal stress sigma n, their resultant force is just pointing upward, which is the sigma V, okay? This is the resultant force. Sigma V is the resultant force of sigma n and tau, okay, and tau. Because all the soil along this direction, soil stress along this direction will be canceled with each other. I mean, because they are the same, okay, they are the same. So the only thing, the tau, the tau and the sigma n, the resultant force can only pointing upward, okay? Can only pointing upward, no horizontal force, okay? The resultant force can only point to upward, which is just used to anti-balance the force, the unit, the weight of the soil mass here. Okay, that's why if we think about the force equilibrium in the vertical direction, we only have two items, sigma V multiply this one and W. Okay, I explained in detail about this one. Okay, and the sigma V is equal to W multiply cosine beta. We just do the simple rearrangement. Okay, and as I said, sigma n tau, this is sigma V, right? As I said, sigma V is the resultant force of sigma n and tau. So sigma n can be written as sigma V multiply cosine beta. This is beta, okay? And tau can be written as sigma V multiply sine beta, okay? This is beta, right? Sine beta is the tau, right? No problem. So with expression of sigma V, we put this one here and here, okay? Then we will have this one, and the W, we already write it here, right? No problem. We put it to replace this W, replace this W. So, okay, we arrived at here. So we have the expression of sigma n and the tau, right? Then then with the definition of the factor of safety in terms of the failure shear strength over current or mobilized tau. Okay, this tau is here, this one, right? And the tau f we use again use the Moore-Coulomb criterion to write it here. Use the effective stress approach. You see, everything is effective stress. Okay, and sigma n we put it here inside, and similarly tau put it here. Okay, we have its expression. Okay, so it's quite long. You see, it's quite a long equation here. Okay, but everything actually step by step. If you slowly. Okay, actually it's not that complicated. Okay, the only thing is the equation seems long, and so sometimes we will assume gamma is equal to gamma saturated. Okay, but of course, as I said, they are not equal, but we can assume it because for simplification purpose, right? So gamma equal to gamma saturated with further simplify. For example, this one is equal to this one, right? They will be canceled, okay? So with further simplify, they will be canceled. We further simplify to here, you see, to here. And if HW is used, you see here, this is HW. HW is equal to Z minus MZ. Okay, this is the height. And it's equal to 1 minus M multiply Z. Okay, if we use this one, if we use HW, okay, we don't want to use M. We use HW to replace the M value, okay? It will be written as here, okay? We just take this Z back to here, okay? Back to here inside. Then to replace the M gamma WZ by gamma W Z minus HW, okay? Minus HW, sorry. Okay, so we get it here. We get it here. Okay, no problem. Actually, we just change the M to HW, right? Okay, change M to HW. So should be okay now. We get it here. So, okay, all the derivation seems quite complicated, okay, step by step, but I just want to clarify with you some important assumption and some important procedure, okay, together in the lecture part. So let's see, if there is a uniform surcharge on top, Q, uniform surcharge on top of this slide, okay, let's see what will happen. Okay, here actually we already have the very general, this one, a very general expression of factor of safety if we use M, okay? Gamma equal to gamma saturated, we further simplify to here, okay? These two are quite important because it is very general for the calculation of the factor of safety. So now we talk about if we have a uniform surcharge on top of this green slice, you see, we have one more item here. Okay, the weight, this I cannot say it is a weight. Okay, I cannot say it is W, is a weight, because weight you see here, in this figure, the weight only represent, the W only represent the weight of the soil. Okay, but here this one actually, even though we still use W here, but it is not only the weight of soil. We have another force, which has the same direction pointing downward, the so-called uniform surcharge on top. Okay, we have this item. So this W is not only contributed by the soil weight. Okay, we have a uniform surcharge. So please not be confused here. Okay, even though we still use W. Okay, but this W is not the soil weight. Okay, they are different. Okay, they are different. So maybe next time I will change to another symbol, okay, to avoid the confusion. So this weight actually contain the uniform surcharge here. One more item. Again, Q is the stress, evenly distributed stress. Multiply the length 1 over cosine beta become a line load, right? A line load. So put together in this equation here, and this W is this one, okay? All the force downward is a Q due to Q and the unit and the weight of the soil, and all the force upward, again, still the same due to the anti-force from the sliding surface. Okay, it's still the same. Sigma V multiplied the length of this side. Okay, so they are equal if we take the force equilibrium along the vertical direction. Okay, and okay, we do the same thing. Rearrangement, decomposition, or resultant force, sigma V. Okay, we discussed already. The only thing is this W now we have one more item due to the surcharge loading on top. Okay, so the final general expression of the factor of safety, we have one more item. You see, one more item due to the Q surcharge on the top. All right, and no big difference actually. Only thing we have one more item. Okay, and so as I mentioned, this is quite a general expression for the factor of safety for this condition, plane translational slip. Okay, and this one is based on the assumption gamma is equal to gamma saturated. Okay, gamma, the total unit weight is equal to saturated unit weight. Okay, based on this assumption, we have the the further simplified equation for the factor of safety. Okay, so with these two equations obtained, we are going to discuss about several special cases. Okay, several different scenarios, like the changing of the water table. Okay, so let's see the one by one. The first one is the dry slope. Dry slope means no water here. There is no water table. It is totally dry. Okay, totally dry. So for this kind of condition, this M will be equal to 0, right? This M will be equal to 0 because no water table, right? And for the dry slope, normally we refer to the cohesionless soil, like sand. Okay, like sand. For this kind of sandy soil, okay, is also possible, right? So for this kind of cohesionless soil, we assume that C prime is equal to 0, and it is totally dry. So C prime and M is equal to 0. Okay, this to just put inside this equation, we arrive at here. Very simple. Tangent phi prime over tangent beta will be the factor of safety. Okay, factor of safety, very simple expression. Let's see. The numerator part, numerator part is determined or depend on the property of the soil, the effective friction angle, right? For example, if it is a sand, like a river sand or the sea sand, this phi might be ranging from 30 to 35, okay, roughly within this range. Okay, but if this soil is like a gravel, okay, like a rock, like more, I mean the boulder, okay, the with a more irregular shape or larger diameter, okay, this phi prime will be larger, even larger than 40 degree, okay. So for this kind of soil, this phi prime actually will be larger, and the tangent phi prime will be larger. Okay, so that if this is constant, the factor of safety will be increased. Okay, and if the beta, I mean the inclination of this sliding slope become larger, okay, become larger like this, like this, like this, of course, we can easily imagine that this slope will become dangerous, right? More dangerous. So if this one become larger, which means F value decrease, right? It becomes more dangerous. Okay, so if you still remember, you visit some dam, okay, dam in Hong Kong. We will use a very big boulder or very big, I mean, some kind of rock, irregular rock, to put. If this is a dam, okay, we will put the rock here, okay, rock here, okay. Use a very big boulder, okay. Because for this kind of boulder, the interaction, okay, the interaction between boulder and boulder actually is quite strong, okay, which means the phi prime is large, okay, phi prime is large, so that we get a higher factor of safety, okay. This is the reason actually. So, okay, we finished the first case. And the second one is a water table at the slope surface. Okay, the water table is just at here. Here, water table is here, which means the slope is totally submerged underneath water. Okay, just at the surface, the water table. Okay, here, and m is equal to 1, right? mz is equal to z, so m is equal to 1. And again, it is if we assume it is cohesionless soil, you see we just put here this one and this one into the general expression. We arrived at here. Okay, and you see this part is the dry factor of safety, right? Tangent phi prime over tangent beta. This one, it multiply gamma prime. Gamma prime is equal to this one. Gamma saturated minus the gamma water, right? Over gamma saturated here. So it means F dry, okay? The factor of dry condition multiply another factor, okay? But this factor, we just use 0.5 to do the estimation, okay? Because gamma prime over gamma saturated is around 0.5, okay? Normally the gamma prime, first of all, we say the gamma saturated only from 80 to 20 kilonewton per cubic meter, okay? So this is for the of the gamma prime to
Please wait for a while. There's a technical issue. We are figuring it out.
All right. Sorry, I just my network has just had some problem, so I leave the meeting. Okay, unexpectedly. Okay, so as Dr. Wu said, we just have uh, maybe around 8 minutes. Okay, break. We will come back at 5:38 around. Okay, and it is still recording. Okay, let's continue. Okay, I don't know why my network was suddenly broken, and now seems okay. So let's continue. As we just said, the gamma over gamma saturated. Okay, normally so for the gamma saturated range from 18 to 20, right? Kilonewton cubic meter. And the gamma prime will be equal to this value minus the gamma w, right? Minus gamma w. So that it's, for example, this one minus 9 point is equal to 8.2, right? Around, I mean. So for this one will be equal to 10.2, okay? The result, I mean, for the gamma prime, kilonewton per cubic meter. Okay, so we just said that this ratio is roughly equal to 0.5. Okay, this is the reason. This is the reason. So you can see for the wet condition, the F value will be, I mean, the half of the dry condition, right? Compared with the dry condition, which means it will be more dangerous, right? And for the third case, the cohesionless slope with water table below the slip surface. Water table is here. Negative pore water pressure suction within the zone is given by this one. The US now is equal to a negative value, gamma W multiplied HS. Okay, negative value. So if we say water table surface here, so the water pressure is equal to 0. Okay, below it, if we say below it, the distance is HS, so the water pressure here will be a positive value, gamma WHS, right? And now, so water table is below the slip surface, which means this one will have an opposite value of this positive value, right? So that we have a negative value here. Okay, always say this is suction. Okay, so for the suction issue, actually, we talk about the unsaturated soil. Okay, unsaturated soil with the effective soil. I mean, the principle of effective stress is equal to this one, right? This one actually is only valid, even though we say this one is very, very important. But this principle of effective stress is only valid for saturated soil, okay, for saturated soil. But here we talk about the unsaturated soil, okay? It will be more difficult and more complicated, okay? But we, of course, we are not going to introduce in detail, okay, about the unsaturated soil. But let's see. If the US here is a negative value, means the pore water pressure here is a negative value, and HS is a vertical distance between the water table and the slip surface, as shown here, right? The factor of safety can then be obtained, okay, right like this. This US in previous general expression, you see, M gamma W Z, M gamma W Z. This is U, pore water pressure. Here, we use minus gamma W HS to replace this item, okay? You see, originally, this one is negative. Now, it is positive, okay? It is positive. Then we arrive at here. If we say again, gamma is equal to gamma saturated, do the simplification, we have this one. Okay, so one negative value becomes positive in the numerator part. Numerator part, okay, numerator part, which means F value will become larger, right? Numerator become larger, F value will become larger, right? From negative to positive, which means if the water table below the slip surface here, it will enhance the stability of this soil slope. Okay, so for the unsaturated soil, we can make some kind of conclusion, okay? General conclusion. I mean, for the unsaturated soil, the soil strength will increase because this suction actually is another resource to enhance the soil stability, okay, to increase the soil strength. Okay, if you are interested, you can read some paper about the unsaturated soil, okay, for the suction. Okay, for example, the soil particle, soil particle, soil particle. If all the void, all the pores are filled with water, that means it is saturated soil, right? But for the unsaturated soil, for example, this soil particle and this soil particle, we have, okay, we actually have the water. This is water. This is soil particle, okay? Here we have the water. Due to the water surface tension, okay, surface tension of the water, this water actually will have a tension force applied on top of the soil particle, okay? So that which will help to stabilize the soil skeleton, okay? The result will be the soil strength increase, okay? Very similar here, we will have a higher factor of safety, okay? Higher factor of safety. Okay, this is water particle tension force. To make these two particles more close, okay, we have external extra force to pull, or to pull these two particles together. Okay, so this is very basic explanation to you about the unsaturated soil. Okay, why the suction actually is helpful. You see, and the cohesionless slope, if seepage through the suction zone parallel to the surface is assumed, which means there is a seepage, a water flow here. Okay, water is flowing here. Then US is equal to this one. This one actually we have already seen it before. Okay, in the original slide, we have no negative sign here. But now, because if the water flow is above the slip surface, we have a positive, right? Positive. But now it is below the slip surface here, water flow. So we have a negative value here. Then where we can write the we just to put this US back to the general equation for factor of safety, and we assume gamma is equal to gamma saturated, and we are here. You see, this one is F dry, if you still remember, right? And 1 plus 1 value. All the value here actually is positive. So it must be larger than 1. Okay, must be larger than 1. So that if there is a water flow beneath, the factor of safety will be increased, right? Compared with F dry. And for the fifth case, submerged slope with no seepage. I mean, the submerged means the water table is higher than the soil surface. Okay. Effective stress are given by the submerged unit weight. Of course, the submerged unit weight actually is saturated unit weight. Okay, let's see. Sigma n, this one, sigma n is equal to sigma v multiplied cosine beta. Okay, similar to here. Okay, I already discussed with you. So sigma v is a resultant force of these two, right? And the sigma v is again equal to omega w multiplied cosine beta, right? Cosine beta to the vertical force equilibrium, right? We get this one. We get this one. We get this one. And again here, the factor of safety is tau F, the failure strength, divided by the current shear stress. Okay. We put this one into here. We put this tau to here, right? We get this one. We get this one. So this one actually, if you compare this value with the factor of safety of dry slope, tangent phi prime, tangent beta, okay? Tangent beta, you see? This one actually can be rewritten. C prime over gamma z cosine beta sine beta plus tangent beta tangent phi prime. Okay, everything cancelled actually. Okay, we move down the cosine to here. Okay, so this item will be written to here. You see, tangent phi prime tangent beta is f dry. Okay, no problem, right? You still remember. And plus one positive value here. So this f value will be larger than f dry. Okay, so if the soil slope is totally submerged underwater, actually the f, I give a name, submerged, okay, is quite large, okay, compare with f dry, of course, as we said here. And f dry actually is around 2 times of f saturated. F saturated, I mean the saturated actually is this case. So water table at the surface, fully wet, okay, it means fully wet. So F submerged is larger than 2 times of F wet. Okay, so that we make some kind of conclusion, you see. When drawdown of the water level occurs, this water level coming down, the exposed slope will develop to case B, F fully wet, and the factor of safety in this region will drop significantly. You see, from here to here. Thus, maintaining water level can be slope stabilization expedient, which means sometimes we pour more water on top of the slope, which will be more safer, okay, compare with the totally dry condition, or of course, compare with the fully wet condition, okay? So for example, if we say like the Three Gorge, I mean the Three Gorge Dam, sorry. I mean in mainland China, Three Gorge Dam, if you know, we have a very big reservoir, right? Very large reservoir. So for example, in the dry season, okay, it is more easy to have the slope landslide, I mean, or debris flow, some kind of this hazard, okay? But if it in the, I mean, in the wet season, the water surface or water table becomes higher, okay? Under this kind of condition, actually, the slope becomes more safer, okay? More safer because we explained here, right? So water submerged, I mean, the slope submerged underwater actually becomes more safer compared with no water, F dry, okay? This is just a case to, I mean, some example for you to explain some kind of engineering background, okay, for all the cases here, okay? And for the undrained condition, which means the phi u is equal to 0, okay? Phi u is equal to 0, like some clay soil, okay? And for this kind of condition, it's very simple. Phi is equal to 0, right? Phi is equal to 0. The only thing left is Cu, the shear strength. Okay, quite similar to what we talked about in, we discussed in lecture 2, right? For the clay soil surrounding the pile, we normally use Cu, okay? We just use Cu, okay? No matter what is the position, the depth of the soil element, we just use Cu, the shear strength, okay? And the tau here is equal to this value, okay, yeah, because we talk about the tau actually is here, right? No problem. So Okay, we finish all the different scenarios. So you can see the relationship. I mean, which one is larger, which one is more safer, okay, which one is more preferable in the engineering practice. Okay, no problem. You can go through by yourself and to digest, okay? And I attach some, okay, this slide actually I just copied from the soil mechanics slides provided by Dr. Andy Leung, okay? Because he already make a good summary about some basic soil parameters for the basic soil type in Hong Kong, okay? CDG, completely decomposed granite, completely decomposed volcanic tuff, okay, CDV, okay, crushed rock fill. This one I just mentioned to you. Just we put some many big boulder rock fill, okay, behind the dam, okay, to increase the dam or the embankment stability, okay. And you see the bulk weight, unit weight. This one actually is gamma, okay. The dry one. Oh, this is saturated, sorry. Dry one, and the phi prime, the C prime, the permeability also, okay, is quite useful. Permeability is also here. CDG, CDV, in situ soil, compacted fill. Compacted fill means the soil we take from other source and we compact it here to make slope or make embankment. Okay, this is compacted fill, or we can say it is a reconstituted soil or remolded soil. Okay, and the in situ soil normally is intact. Okay, intact. This is intact soil. But for the compacted soil, compacted field, we will have some compaction energy, right? Like a Proctor test. Proctor test. You still remember? In the soil mechanics, we apply the compaction energy to make this soil more dense. You see, the unit weight becomes larger, right? Becomes larger. Okay, this one becomes larger because we apply the compaction energy. You see the friction angle becomes larger, okay? I mean, the minimum value is larger, you see? Okay, and the permeability becomes smaller, you see? Permeability becomes smaller relative to here, compared to here, because the soil is more dense, densely compacted, okay? The void becomes smaller, so the permeability becomes smaller, okay? And so here shows you some very typical value, okay? As a geotechnical engineer, okay? For example, all the values here you should bear in mind, okay? Very quickly you can respond to others. What is the typical value for this kind of typical soil, okay? This is what we should have, okay? This kind of concept. So I prepare some videos here to show you the Summer Pain landslide in 1972 and 1976. I guess some of you has already know, okay, but we can just watch the video here.
Hong Kong is one of the most densely populated areas in the world. With land at a premium, development and construction work has to proceed in and around hilly locations or near steep terrain. Combined with subtropical climate bringing warm and wet summers, this makes Hong Kong prone to flooding and landslides. On the 18th of June 1972, after a period of heavy rain, more than twice the average for the time of year, two major landslides occurred. At approximately 9 p.m., a hillside failed above Po Shan Road on Hong Kong Island, causing a catastrophic landslide, which claimed 67 lives. Over in Sao Mau Ping in the Kwun Tong district, the story was much the same. In the 1970s, this area was home to many families of low income, some of whom inhabited simple huts on the steep slopes. On that fateful day, the rain was relentless all morning with an exceptionally heavy downpour around 11 a.m. By 12:30, Choi Ping Road in front of a licensed squatter area at the base of the fill slope was already flooded. At 12:40, earth was seen coming down the fill slope. Less than half an hour later, the disaster happened. Described as sliding down like a carpet, the 40-meter-high fill slope collapsed onto the huts in the licensed area, engulfing them in earth and pushing everything in its path across Choi Ping Road and into the Kwun Tong resettlement estate. All in all, 71 people lost their lives. The devastation was comprehensive, and the licensed squatter area was completely covered in mud, up to 3 meters deep in places. The forensic investigation concluded that the landslide was primarily due to the softening of the fill material, caused by infiltration of rainwater, mainly through the sloping face, as a result of an exceptionally long and intense rainstorm. Some 4 years later, a short distance away, another fatal landslide happened. Just 200 meters from the 1972 landslide, on the 25th of August 1976, another fill slope failed in similar circumstances. Tropical storm Ellen had battered Hong Kong for 2 days, causing widespread landslides across the territory. At around 9 a.m. on the 25th of August, the slope above Block 9 of Sao Mau Ping Estate suddenly collapsed during a heavy rainstorm. The wet mud poured into the lower floors of the block, killing 18 people and injuring 24. A number of cafes and shops were destroyed by the mudslide, which required the subsequent evacuation of 2 residential blocks. Investigation concluded that the embankment fills were too loose to withstand the weakening effect of the preceding severe rainfall infiltration, leading to the fatal landslide. Today, looking at the tranquil parks and safe and secure established slopes where the catastrophic landslides took place, it is hard to imagine the damage and losses that took place in this area of Sao Mau Ping. The disasters brought about radical changes to geotechnical engineering in Hong Kong, and in 1977, the government created what is today the Geotechnical Engineering Office. This office continues to serve the people of Hong Kong to ensure that disasters like the Sao Mau Ping and Po Shan Road landslides will not occur again.
All right, this video shows you 2 catastrophic disasters happened in the history of Hong Kong, and the reason why Hong Kong government established GEO, okay, back in 1970s. Okay, as I mentioned to you, Professor Morgenstern is the founding member, okay, to help Hong Kong government to establish the Geotechnical Engineering Office, okay. And as you can see, with after the establishment of GEO, the fatality, okay, the number of landslide fatalities each year actually decrease significantly, okay. So because Hong Kong government invests a lot of money in the stabilization of slopes, and actually until now, the slope stabilization and the slope safety monitoring, and also the measurement techniques about the slope stability. Actually, in Hong Kong has become one icon, okay, one icon in the geotechnical engineering around the world for Hong Kong, I mean. So you see more than 25,000 cut and fill slopes in hilly terrace formed before 1977, and more than 0.8 billion Hong Kong dollars spent every year, okay, every year on the slope upgrading. And about 80% of the slopes in Hong Kong is stabilized using soil nails. Okay, so soil nail actually is very important in Hong Kong's geotechnical engineering field. Okay, so here shows you another video about the installation process of soil nail.
Boreholes are drilled in accordance with the depth and angles determined by the project. Depending on the depth and diameter of the hole and the characteristics of the work area, drilling can be performed using portable or wagon drillers. Water, injected through drilling rods, is used as a drilling fluid and for cleaning the hole. The first phase, called sheathing, only fills and reconstitutes the excavated space to execute the hole. The injection grout is prepared in high-shear colloidal mixers. Nails are pieces molded in situ that retain and consolidate a mass of unstable soil by injecting cement grout over its metal structure. The tension-resisting nails or nailings are produced by inserting a metal bar and injection tubing into the soil. The cement grout is injected into the tubing under pressure in as many phases as necessary. Another detail of the injection demonstrates Solotratti's excellence. Throughout the process, data regarding the maximum pressure and volume of cement grout absorbed is collected. This permits, via graphics and projections, the geological mapping of the site. The result? More and more solid construction, executed in less time and with reductions in cost.
Okay, so we watched this video for the installation process of soil nail. So you see here shows you the cross section of the soil nail. Okay, this figure is prepared by GEO in the geotechnical design menu. Okay, so you can see that here is a rebar. This one is a rebar. Okay, it can be steel rebar, or it can be GFRP, or even CFRP. Okay, fiber reinforced polymer. Okay, glass or carbon fiber reinforced polymer. Okay, these two are new material. Okay, but actually it has been quite commonly used in different areas of civil engineering. And here, normally we will use a steel rebar. Okay, but I think now the government also and as well the engineers are looking for, I mean, the feasibility to prove the feasibility to adopt this kind of GFRP in the soil to replace the steel rebar, because this one actually has no corrosion problem. Sorry. Okay, no corrosion problem. It's quite stable, and the tensile strength is higher than the steel rebar. Okay, but the carbon one, actually the tensile strength is much more higher, but the expense, the cost is of course is much more higher than the GFRP and the rebar, steel rebar as well. So normally we will use steel rebar here, and you see we will drill a hole first using the water as the fluid to clear some debris in the hole out. Okay, and we will put this kind of packer here to make sure the steel rebar is just at the center position of this hole. Okay, to hold it to hold it, and then we will to insert the concrete. Okay, the concrete. Insert the concrete as mentioned in the video. Sometimes we will not just simply insert or pour down the concrete. We will apply pressure. Okay, so we can say this method called the pressurized grouting. Okay, pressurized grouting. For example, we will use 100 kPa or 200 kPa even to apply the pressure on the concrete grouting. Why? Because if we have a higher pressure, because the surrounding is soil, right? The higher pressure under this kind of condition, the grouting concrete will penetrate to the soil body, to the soil mass, penetrate, because there are voids inside the soil, so that the bonding effect between the concrete and the soil will become larger, will become more significant due to we have some penetration of the grouting. Okay, so then we will have the soil nail head installed using some nut, right? Using some nut to fix it at the top. And then you see here, we will use another concrete to make this soil nail head more stable, okay? Because this is a slope. We'll use the concrete to concrete, the soil nail on the slope, okay? And this is the detail, okay? The process of installation of soil nail. So here we show you some text, okay? You see, you can read it by yourself. And the advantage of soil nailing, the cost is low, okay? It's only 50% of the tie-back wall, okay? Tie-back is another method of stabilization for the slope, okay? It's another method, and the soil nail is only half of the cost. The rate of construction can be very quick, and the phase inclination, because we will use the shotcrete, like the concrete will be spray, okay, on top of the surface of the slope as a facing, okay, which will increase the overall stability. That's why we will say, okay, the facing inclination can be increased, okay, can be increased. The deformation behavior and the design feasibility is high. The design reliability in saprolitic soil, okay, the reliability of soil nail in this kind of soil is high. The saprolitic soil means chemically weathered soil, okay, in Hong Kong. So you see, more robust and reliable design on the soil, difficult soil condition. Okay, this is an advantage of soil nail. And here you see, normally the soil nail will be installed at an angle of inclination from 10 to 20 degree, okay? From 10 to 20 degree, okay? And the thickness for ordinary steel bar, you see, steel bar, a thickness of 2 millimeter is assumed as the corrosion zone, so that the design bar diameter is totally 5 millimeter less. Okay, this is very important. We will utilize for calculation later, okay? You see For example, the diameter of this steel rebar is 16 millimeter. I mean the diameter. Okay, so for the more conservative design purpose, we only regard this steel rebar has a diameter of 12 millimeter. Why? Because 4 millimeter, 2 millimeter on each side, we think it is already under corrosion process. Okay, so we think the diameter will be decreased due to corrosion effect. Okay, so the diameter will become 12, for example, from 16 millimeter. Okay, and we emphasize one more issue is the difference between the soil nail and anchor. Okay, the biggest difference is soil nail is a passive way to stabilize the slope. The passive way means we install the soil nail on the slope. Okay, if the slope has no movement, okay, has no movement, the soil nail will not exert force on the slope. Only after the soil slope has an intention to slope or have already moved a little bit, the soil nail will insert anti-force to stabilize the slope. Okay, this is the meaning of passive. But for active one, which is the anchor condition, okay, anchored because it is pre-stressed, like pre-stressed concrete, okay, we will have some to apply some pre-stress through some method, okay, to for example, have a nut here to apply the pre-stress. So inside the anchor itself, it is already existing some tensile strength inside. Even the soil slope doesn't move. Okay, so anchor, because of the pre-stressed force, it is an active way to make the soil slope stable. Okay, but the soil nail is a passive way. Okay, this is the main difference between soil nail and anchor. Of course, we emphasize some limitation. Okay, for example, the vertical movement we induce. Okay, because it is a passive way. Okay, rather than the effect rather than the active way like the anchor. Okay, and difficulty in installation on the groundwater action means because we are going to drill a hole. If there is a water below the water table, the water will come out. It's very difficult for us to fill the concrete and to make the hole very, complete. Okay, because this hole will collapse due to the soil, the water movement. Okay, it's very possible. And of course, it's similar. It's very difficult for loose fill. The reason is the same because we are going to form a hole first. If it is very loose, the hole itself will collapse. Okay. And another reason is for loose fill. Actually, we will have the concrete inside, but the concrete, the interface between concrete and the fill will be very weak, okay, because the fill here is very loose, okay, so the interface strength will be very loose, very weak. So we will talk about this in the so-called interface strength later, okay, through some calculation, okay. Right, so we still have some time you can see here we apply a new item called TS on the slope. Okay, this black one is a soil nail. Okay, I just draw it like this. Okay, the soil nail head and the soil nail itself, you see. And this one actually will exert a force which is equal to TS to the green mass of slope. Okay, the green mass is the moving body, right? The sliding body or rotation body of the slope sliding, So let's see. We have the mobilized shear stress which is equal to the tau f over factor of safety. Tau f here is expressed by the Moore-Coulomb criterion, right? Criteria. And the factor of safety is here. If the phi u is equal to 0, we use the Cu, like a clay soil, right? This is a simplification, okay? And we take the moment equilibrium, okay? Moment equilibrium. Let's see. What is the driven moment and what is the resistant moment? The weight of the soil mass, the moving mass of the soil weight, multiplies the lever arm, means the distance between the resultant force of the weight of the whole body to the rotation point, center. This is a D, right? This is a driven moment, okay? And the tau m multiplies the whole length of the slipping surface, the length of slipping surface is a force, right? Multiplies the lever arm or the moment arm here, R, okay? Because we assume this circle, this surface is a circle, okay? So all the distance to the rotation center is equal to R, right? Equal to R. Okay, this is resistance moment. Now we have one more item, Ts multiplied ds. ds is the resultant force due to the soil nail to the rotation center. Okay, you see we have two items now for resistance. So that you see the factor of safety, we have a negative item in the denominator part, which is induced by the soil nail. Okay, so denominator becomes smaller, f value become larger. Okay, this is okay the reason why the soil nail will help to increase the stability of the slope, because f factor becomes larger, right? And of course, the searching method is the same. Searching method is the same. We assume the slip circle and to find the different f values and to determine the minimum f value. Okay. And here we apply, here we have no slice of the soil, right? But here we can divide the soil slope into different slices. 1, 2, 3, 4, 5, 6, 7, 8, right? So into 8 slices, we take out one slice as an example because we will not only install one soil nail, right? So for example, on the slice 5, we have one soil nail, which is TS. This I means the number, okay, the number of the soil nail. For example, another one is here. So this one is TS1, another one is TS2, okay? So this TSI is applied at this position. The inclination angle is beta I, okay? And let's see, we should make, again, we find the equilibrium of moment, okay? So the T is force given by the soil nail, right? And this, oh sorry, this T soil nail is here. TSI multiply DSI. The distance is here. Okay, this is a resistant moment into this direction, right? This direction. And this T is a shear force, okay? Shear force, which is equal to tau m, this one, right? Tau m multiply LA, right? Tau m multiply LA, the length, okay? This is the shear force, and the driven moment is still the weight due to the gravity of the soil mass. We W multiply R, the level arm multiply sine alpha. Okay, we already discussed this. So we have 8 slices. Actually, we should sum up 8 different sections. Okay, so we have this integration sign here. Okay, and the tau T actually is a tau m, as I said. Tau m is equal to tau f divided by f, right? Here. And then multiply L, which means because we will divide, we just, for example, we look at this one, okay? For this one, the tau m, okay, let's say tau f divided by F, then multiply L. L is the length of this side. Now it becomes the force, line force or line load, okay, for the separate slice, okay, for the separate slice. But here actually you will see the R actually is, okay, no R, because we divide R for the both side of this equation. So that you see this here, we have a R here, right? We have a R here. Okay, we move this item to the right-hand side, we get this one, okay? And F, the factor of safety, can be after some rearrangement, okay? After some rearrangement, the F factor is here, can be taken out, okay? Why? Because at the beginning of this lecture, we say F is a lumped factor, okay? Lumped factor, which means it considers all the conditions, all the factors. We only have one factor to represent the factor of safety for the whole slope, so that this F value is a constant value for all the slices. So it can be taken out, okay? It can be taken out to here. So tau F W, this one, the tau F can be, okay, written here according to the Moore-Coulomb criteria. So slope, step by step, this L for this C prime can be taken out after integration, because it means the whole length, actually, the whole length, because this C is a constant. If the soil property is uniform, it can be directly taken out, and summation of L is equal to LA, right? So total length of the failure surface is equal to LA. And tangent phi again can be taken out because it is a constant, right? And the sigma n prime L, sigma n prime L is this one, stress multiplies the length is equal to the total effective force. The alpha actually we know, because for each slice, for example, this one, we can measure alpha. For example, this one, it has another alpha, but we can measure directly through the geometric method, okay? We can measure it. So alpha for each slice we know. TS we can calculate, okay? We can calculate, for example, how much is the force exerted by the soil nail, and the DS, of course, we can measure it from the geometrical way, and R actually we know it because everything we know, okay? Phi we know, but how about n prime, okay? The problem, again, come back to how to express the n prime here, okay? Again, the problem, again, come to this parameter, n prime, okay? So different researchers have different methods for n prime for this one. For example, for the Bishop routine solution, it assumes the vertical resultant force is equal to 0. Vertical 1, x1, vertical 1, x2 is equal to 0. x1 is equal to x2, okay? So minus x2 will be equal to 0, no problem. The total shear force T at a slice base here, this one is, okay, we discussed this one already for several times. And resolving the force in the vertical direction, you see the purple arrow, vertical direction. For pointing downward, let's see. The first one is the gravity of the soil due to the self-weight, right? And another one is the force exerted by this soil nail. You see, it can be decomposed into two parts. The first part is this one. So if this angle is beta I, so this downward force is equal to TSI multiply SI beta I, right? No problem. And this too is the force downward. How about the force upward? Okay. The M prime here. Then, okay, and this one multiply cosine alpha will find the decomposed force along the vertical direction due to the normal stress or normal force, okay? Another part is the pore water pressure also will exert an upward force. You see, also cosine alpha. Okay, another one is the T, the tau. This T is not the solenoid force, okay? It's the tau, it's a shear force. Then this one also has an upward decomposed force, you see? And this one, this is alpha. So this value is equal to T multiplied sine alpha, okay? So, okay, one by one. This is normal force. Okay, this is powder pressure. Oh, this is normal force. Okay, this tau divided into two parts. Okay, you see here. Okay, this one. We get it here. So this T will be divided into two parts. Okay, so we only have one n prime here. After some rearrangement, okay, we have the n. Put this n prime to here. Okay, we have this long equation again. Okay, so you see here on the right hand side we have one f. On the left hand side we have one f. So again, we will use the iteration method to determine the real f. Okay, normally it will converge very quickly within 3 times of iteration. Okay, you will have quite a stable f value. Okay, normally. So you see here, this is the f, this is the f, right? We use the iteration method. Okay. Let's see. Okay, the time is up. Maybe I will stop here today. Let's see how much left. Okay, so I think we may need to speed up, okay, next time. So because some place I prefer to explain in quite detail, okay, to help you to understand. But the time seems a little bit limited, okay? So maybe we need to speed up next time. So far, do you have any question?